This is Spacetime Series 25, Episode 41. Coming up on Spacetime, looking at how Pluto's giant ice volcanoes could have been created, how ice on Mars is providing clues about the red planet's climate history, and monitoring the shrinking ice coverage on planet Earth. All that and more coming up on Spacetime.
Welcome to Spacetime with Stuart Gary.
A new study suggests that the giant cryovolcanoes seen across the surface of the frozen distant world of Pluto were created through multiple eruptions, the likes of which have never been seen anywhere else in the solar system. The findings, reported in the journal Nature Communications, shows that material expelled from below the surface of this distant icy world could have created a unique region of large domes and rises flanked by hills, mountains and depressions. The study's lead author, Kelsey Singer, from the Southwest Research Institute in San Antonio, Texas, says the unique geological formations seen on Pluto haven't been found anywhere else in the solar system. Singer says rather than erosional geological processes, cryovolcanic activity appears to have extruded large amounts of material onto Pluto's exterior and then resurfaced an entire region of the hemisphere which was imaged by NASA's New Horizons spacecraft. New Horizons visited the Pluto-Charon binary planetary system and their four moons, Styx, Nix, Hydra and Kerberos, during their historic flyby in January 2015. Singer's team analysed the geomorphology and composition of an area located southwest of Pluto's bright heart, Sputnik Planitia. This cryovolcanic region contains many large domes ranging from 1 to 7 kilometres tall and 30 to 100 or more kilometres wide, some of which appear to merge into more complicated structures. Irregular interconnected hills, mounds and depressions called hummocky terrain cover the sides and tops of many of the larger structures. Importantly, few if any craters exist in this area, indicating a geographically young surface. The largest structures in this region rival Hawaii's Mauna Loa volcano. Even with the addition of ammonia and other antifreeze-like chemicals to lower the melting temperature of water ices, a process similar to the way road salt inhibits ice forming on roads and highways, the extreme low temperatures and atmospheric pressures on Pluto still rapidly freeze liquid water on the surface. Because these are young geologic terrains and large amounts of melted material were required to create them, it's possible that Pluto's interior structure retained heat until relatively recently, thereby enabling water ice-rich materials to be deposited onto its surface. Cryovolcanic flows capable of creating large structures could have occurred if the material had a toothpaste-like consistency, behaved somewhat like solid ice glaciers flowing on Earth, or had a frozen shell or cap with material that was still capable of flowing underneath. See, the problem is the authors couldn't find any other geological process likely to have created these sorts of features. For example, the area has significant variation in altitude, which is unlikely to have been created through erosion. Singer and colleagues also saw no evidence of extensive glacial or sublimation erosion in the hummocky hill terrain surrounding the largest structures. Singer says one of the benefits of exploring new places in the solar system is finding things like this, which are completely unexpected. These giant, strange-looking cryovolcanoes observed by New Horizons are a great example of how science is expanding its understanding of volcanic processes and geologic activity on icy faraway worlds. The images obtained by New Horizons have revealed diverse geological features right across Pluto, including massive mountain ranges, incredibly deep valleys, as well as vast plains and glaciers. They're especially intriguing because the frigid temperatures at Pluto's distance from the Sun meant things were expected to show very little geological activity. This is Spacetime. Still to come, ice on Mars providing clues about the red planet's climate history, and monitoring the shrinking ice coverage on planet Earth. All that and much more still to come on Spacetime. A new study has found that just like Earth, ice deposits on Mars show the red planet's climate is strongly controlled by changes in the planet's axial tilt and orbit around the Sun. The findings, reported in the journal Geophysical Research Letters, are based on images from the HiRISE high-resolution camera aboard NASA's Mars Reconnaissance Orbiter spacecraft. Understanding the relationship between Mars's climate and its axial tilt and orbital path are some of the most important goals of Martian science. Most past studies towards this goal have looked at the polar ice caps, huge sheets of water ice and frozen carbon dioxide found at the planet's north and south poles. To gain more insight, the study's lead author, Michael Sorry from Purdue University, together with colleagues, instead studied smaller ice deposits located deep inside craters. These craters were only tens of kilometres wide, located near the north and south poles, but they were separate from the larger polar ice caps. The authors used computer software to study the shape of layers in the ice deposits and compared patterns in the layered shapes to known variations in Mars's orbit and its axial tilt. Sorry and colleagues found that ice deposits in Burrow Crater contain good evidence that recent Martian climate is strongly controlled by changes in the planet's orbit and in its axial tilt. This report from NASA TV.
Beneath the thin atmosphere of Mars lies an enigma, a desert landscape shaped by flowing water. In the distant past, Mars must have had a warmer, wetter climate, but scientists wonder just how wet was ancient Mars?
So in the ancient past, we have some indications of water was flowing on the surface, but how much water was there? We're talking about oceans, are we talking about small rivers, little rain? So these definitions of how much water was on the planet was very undefined.
A major question has been how much water did Mars actually have when it was young, and how did it lose that water?
To answer this question, a team of researchers at NASA's Goddard Space Flight Center used infrared telescopes on Earth to study water molecules in the Martian atmosphere.
We used the world's 3 major telescopes for infrared astronomy. From the ground, we could actually take a snapshot of the whole hemisphere of the planet on a single night.
The new infrared maps reveal the atmospheric ratio of normal to heavy water molecules at different locations and seasons on Mars. Heavy water molecules contain a heavy isotope of hydrogen called deuterium, which remains trapped in the Martian water cycle, while normal hydrogen is lost to space. The researchers found that water from the polar ice caps is highly enriched in deuterium, indicating that Mars has lost a tremendous quantity of water.
Now we know that Mars water is much more enriched than terrestrial ocean water in the heavy form of water, the deuterated form. Immediately, that permits us to estimate the amount of water Mars has lost since it was young.
The findings indicate that only 13% of an ancient ocean remains on the planet today, now stored in the polar ice caps. 87% of this ocean has been lost to space. This means that early Mars would have looked much different than it does today, with a significant portion of its surface covered by water.
So the really interesting question is, could it form a sea or an ocean? And indeed, it would. In the northern plains, which is a relatively flat region but depressed from the rest of the planet, it would form an ocean that was approximately 20% of the planet's surface area. And so that is a respectable ocean.
This ocean had a maximum depth of around 5,000 feet or around 1 mile deep. It's deep, not as deep as the deepest points of our oceans, but comparable to the average depth of the Mediterranean Sea.
By combining Martian topography with the new estimate for water loss, the researchers were able to simulate Mars's ancient ocean and its escape to space. As Mars lost its atmosphere over billions of years, it lost the pressure and heat needed to keep water liquid, causing the ocean to shrink and recede northward. The remaining water eventually condensed and froze over the north and south poles, giving Mars the ice caps that we see today. This new scenario means that Mars would have stayed wet for longer than previously thought, expanding its ancient habitability.
We now know that Mars was wet for a much longer time than we thought before. Curiosity shows it was wet for 1.5 billion years, already much longer than the period of time needed for life to develop on Earth. And now we see that Mars must have been wet for a period even longer
It's fascinating that we can learn so much about 4.5 billion years ago with measurements taken right now. And ultimately we can conclude this idea of an ocean covering 20% of the planet, which opens the idea of habitability and the evolution of life on the planet.
This is Spacetime. Still to come, monitoring the shrinkage ice coverage on Earth, and later in the Science Report, a new study shows that you really can blame your parents if your academic performance at school isn't the best. All that and more still to come on Spacetime. Last week's report that weather stations in Antarctica are showing temperatures 40 degrees Celsius above normal for this time of year have triggered alarm bells around the world. Concordia Station, located some 3,234 metres above sea level on top of Dome C on the Antarctic Plateau, is best known for being the coldest place on Earth. Last week it recorded an all-time high temperature of minus 12.2 degrees Celsius, but that record's now been broken again, with a temperature of minus 11.5 degrees Celsius. Now, for the record, normal average surface temperatures at Concordia for this time of year are around minus 49 degrees Celsius. Robert Rohde, the lead scientist at Berkeley Earth, described it as a new world record for the largest temperature excess above normal ever measured at an established weather station. And Concordia wasn't the only place to record record warm temperatures on the frozen continent. The Terra Nova Bay station on the Antarctic coast recorded a balmy 7 degrees Celsius. And further inland at Vostok station, they reported a high temperature of minus 18 degrees Celsius. That's some 17.2 degrees warmer than the average for this time of year, and almost 3 degrees Celsius warmer than the previous record. Now, these Antarctic heatwave conditions, for want of a better term, are being blamed on a massive high-pressure system over the Southern Ocean southeast of Australia, which is driving a warm moist air stream reaching down across the Antarctic. But Antarctica isn't alone in what's happening. At the other end of the planet, the Arctic's also experiencing average temperatures 30 degrees warmer than usual. Norway and Greenland are both experiencing unusually mild winters. And the International Panel on Climate Change says extreme heat events have increased in the Arctic since 1979, and it's likely to cause ice-free summers across the Arctic at least once every decade, once global warming hits 2 degrees Celsius above pre-industrial levels. Weather models by the United States National Oceanic and Atmospheric Administration, NOAA, show the Antarctic continent as a whole are some 4.8 degrees Celsius warmer than its baseline temperature between 1979 and the year 2000. At the same time, the Arctic as a whole is 3.3 degrees warmer than its 1979 to 2000 average. And as for planet Earth as a whole, it's also now 3 degrees Celsius warmer than the 20th century average. Keeping track of these ever more alarming figures is a constellation of weather satellites and scientific spacecraft maintaining an ever-vigilant eye over the Earth below. This report from ESA TV.
Climate change is impacting our planet and society as never before. This is why the European Space Agency is using Earth observation satellites to measure and determine the consequences of human activity on a global scale. One of the most damaging effects seen from space is the global trend of melting ice on our planet. This ice is called the cryosphere. It's comprised of ice sheets such as the Antarctic, sea ice like in the Arctic, but also of glaciers and permafrost regions. While the melting of the ice sheets of Antarctica and Greenland are the best known examples, satellite measurements indicate that in the last half-century, glaciers across the globe have also lost a significant amount of ice.
Over the course of the last century, we've seen quite dramatic changes in these different elements of the cryosphere. Notably, we've seen significant losses in Arctic sea ice. We've seen decline in the volume of ice locked up in glaciers. And we've also been witnessing changes in the large ice sheets, Greenland and Antarctica. The consequence, of course, is that sea level is rising as water is transferred from ice on land into the ocean.
While half of the sea level rise comes from thermal expansion caused by warming ocean water, melting glacier ice is the second largest contributor. Research shows that over the last 50 years, glaciers have lost more than 9 trillion tons of ice, raising the sea level by 2.7 centimetres. Although yearly data measurements may fluctuate, a global trend is visible whereby the rate of ice loss has increased. At the current rate, about 3 times the volume of all ice stored in the European Alps is lost every year. This corresponds to around 30% of the current rate of sea level rise. While rising sea levels are threatening many coastal areas across the world with severe flooding and more extreme storms, melting glaciers will also impact people living downstream of these glaciers, who depend on this seemingly eternal water resource, especially during the summer or dry season.
Glaciers have a huge impact on the population on Earth, in particular in Southeast Asia, where millions of people are dependent on mountain water resources. During the summer season, we see the melting of the glacier and the mountain snowpack. This, of course, releases water, which is used for irrigation in the fields. It's used for generating hydroelectric power, and it's also used for drinking water. And so we're very much concerned with how climate warming has an impact on the seasonal stream flow and the way in which the water resource can be managed in the future.
From space, several of ESA's Earth observation satellites and the EU's Copernicus satellites monitor our global ice cover. Cryosat, for instance, is dedicated to measuring the thickness of polar ice and changes in the ice sheets of Greenland and Antarctica, whereas Sentinel-1 is used to track sea ice. With this kind of satellite data going back more than 25 years, scientists can calculate the volume of ice loss on a global scale. It also furthers their climate models and allows them to make predictions about the rate and impact of future ice loss. Another worrying aspect of the global thaw is the impact it has on permafrost. This is the almost permanently frozen ground around the Arctic regions. Scientists are concerned that when this ground thaws, methane that was trapped in the soil will be released into our atmosphere, amplifying the greenhouse effect. But it's not the only self-replicating effect being triggered by the melting of snow and ice.
We talk about the impact of melting snow and ice surfaces in terms of what's known as the albedo effect. When snow is dry, it's very reflective, and of course that helps to reflect sunlight back out into space, and the consequence is we can reduce the amount of melting this way. However, as ice and snow melt, the albedo and the reflectivity becomes lower, and this has the effect of absorbing more of the solar energy. This contributes to further warming and further melting. And so it's a runaway progressive effect caused by the reduction in the albedo.
It's clear that monitoring our planet's cryosphere is of great importance, as it influences the lives of millions of people. The European Space Agency recognizes this and already looks forward to the future. 3 of the 6 high-priority candidate Sentinel missions are aimed at addressing urgent climate and operational user needs related to ice sheets, snow, and sea ice. With these tools, from space, we can look at our planet and see which policies are needed to slow the global thaw.
And in that report from ESA TV, we heard from Mark Drinkwater, the head of the European Space Agency's Earth and Mission Science Division. This is Spacetime. And that's the show for now. Spacetime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favorite podcast download provider, and from spacetimewithstuartgary.com. Spacetime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the Spacetime store for a range of promotional merchandising goodies. or by becoming a Spacetime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more Spacetime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our Spacetime YouTube channel, and on Facebook, just go to facebook.com/Spacetime with Stuart Gary. And Spacetime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to Spacetime with Stuart Gary. This has been another quality podcast production from Bytes.com.